Okay, with that, it looks like we have a good amount of people that have come in. We thank you for all coming. We're really grateful for all the input that we can get, and we really appreciate your time. So with that, I guess we can get started for our preliminary design review for MASA-Dearborn. This year's project is called Project Up or Under Pressure, and that has to do with our payload, which we'll talk about later on. So let's start with an overview of what we'll be talking about. So we'll just be doing our team overview, competition overview, some team goals, along with some rocket overview and con-ops as well. A majority of our PDR will be the subsystem overview, along with a 5-minute intermission. And then we'll be doing project management at the end, along with any questions. We ask that you just save them towards the end so that we can discuss them in more detail. At the end. All right. So here's our team member breakdown for this year. We have 49 members, 32 men, 17 women. A majority are mechanical and electrical engineers. You can see we actually have some bioengineering and mechanical engineering, along with computer and robotics, and then 4 other who are on project management. 17 of the members are returning members from the previous competition year that have gone to competition. So here's a list of our certified flyers for this year. You can see we have 1 level 2 right now, and soon to be 3 level 2s. That'll be me and Josh coming soon, along with Andre and Perla and Alia as level 1. Along with this, we will actually be having our certification class this year, as we did last year. It'll be led by Sierra, and we'll be doing open rocket classes and CAD tutorials, and we'll be launching at Alke Airport November 19th. And we'll have 20 new flyers who will be able to get L1 certified. So we're hoping to get 20 new members this year after November. So that'll be a really good boost for just our knowledge base and getting everyone experienced in rocketry. So we're really excited for that. So here's our team structure. You have me, Devin Neimer, as president. John Florin is the mechanical lead. Andrea Maldonado is the electrical lead. Perla Ferris is the project manager. And Jamal Kazada is our safety and launch operations lead. So each year we compete in Spaceport America Cup. The competition is to bring a payload to a target apogee. We'll be competing in the commercial off-the-shelf 30,000-foot category this year. So the target altitude is 30,000 feet, and our motor will be bought through a vendor, not made by students. So our location, that'll be in Spaceport America near Las Cruces, New Mexico, from June 19th to the 24th in 2023. So it's hosted through ESRA, and sponsoring agency is Spaceport America. So this is a new category for us, and we're really excited to take a new step into this 30,000-foot category. So here's a point breakdown from the previous year. You can see the 2021-2022 score that was our results, and then this is what we project on the far right for 2022-2023. So you can see a big step that will actually give us a lot of bonus points will be launching early. We hope to launch early this coming year, and that'll gain us 100 extra points, along with some minor improvements to design, technical report, and scoring on flight performance. That'll really improve our score, and that'll really give us the boost we need for this year. So you can see on the far right, I wanted to mention that we did win the Dr. Gilmore Award for Innovation this year for a couple different things. It was for our L1 cert class, and it was for an innovative design for our air brakes, the mounting system, along with a student research and develop flight computer. So each year we develop our goals for the year at the beginning of the season. So this year we want to launch a competition the first day. Like I said, getting those bonus points, retain 25 new members, place top 15 overall, and get 20 members L1 certified, along with 5 members L2 certified. Here you can see our vehicle architecture from the Dart to the booster. So we actually have a boosted Dart configuration this year. It'll just be a single stage with one motor, but it'll actually separate by drag. And we'll go into that a little bit more in the airframe section, and you can see all the different components that we'll be going over more in detail in each project overview. So here's a comparison of our rocket from the previous year to this year. Our payload experiment, it was a valve actuation experiment. Now it's a data gathering and body tube strain experiment, and we'll explain that a little bit further later on. So it was a 6-inch diameter. Now we're switching to a 5 to 3-inch diameter. So it's transitioning from a 5 on the bottom in the booster to a 3-inch in the dart. And then CubeSat payload is not possible this year. If we wanted to get extra points, we wouldn't be able to due to the 3-inch diameter. Also, we'll have more COTS microcontrollers in our payload this year for reliability. Since we have a newer electrical team, this will be very useful for us. We also have airfoil fins with our new 30,000 foot apogee. We found that would be very useful for our flight. And then some similarities are the air brakes, a similar design or slightly different design, but similar application. Electronics for recovery are going to be the same, along with our tele-GPS will be the same. And then we'll also have COTS body tubes and nose cones. So here's our payload summary. It's a body tube strain and data collection experiment. So the main goal is to retrieve reliable and accurate flight data. That's kind of what we've wanted to gain in the past, and we want to have a reliable way to give us data on how our flight went and give us information for next year. So sensing things like velocity, acceleration, temperature, we've done before, but we want to see humidity, and also the big one is strain on the body tube. So we want to see what sort of strain forces on that body tube in the dart are occurring. So some benefits, you'll see that we'll have future airframe design improvements, and some previous launches have left more to be desired in terms of data collection. So once again, COTS microcontrollers will help with reliability for that. So here's our launch vehicle summary. 153 inches or 12.75 feet. So we'll actually have two different motors, one for testing and one for the 30K launch at competition. So the M3400 will be used for, which is a lower class M motor. It'll be used for our test launch, so we can stay below the flight ceiling. The O3400 will be for our 30K launch. You can see our recovery system will be a reef parachute system to save space. And finally, here's our timeline. You can see some key points and milestones that we actually have in our timeline. We began in June with our e-board elections, and then we have gone down to October now, where we are at PDR. And after that, we'll be gearing up for our first season phase in manufacturing. And then also just some competition outlines if you'd like to read further. We sent these slides out, so feel free to view.
Hi everyone, I'm John Florin. I'm the mechanical lead. I will be taking you through the team structure, our systems engineering, our ConOps, and our mass distribution. So we saw a little bit of the team structure, and here's a further breakdown. Our electrical and mechanical teams are both overseeing our payload, recovery, and airframe teams this year instead of breaking off into more electrical subgroups. This will help us stay more intertwined when we discuss how our electronics are integrated. And we also have developed our project management team. So I'm going to take you through the different sections of our rocket, starting with our upper dart. At the tip of our upper dart, in the nose cone, we're going to have a tele-GPS, where it will avoid interference of the metal frame structure of the payload. Then we'll have our payload to house all the data collection electronics. We'll also have a camera system mounted at the bottom of this payload, and below our payload we will have our dart parachute, which will be reefed. Below that, we are going to have our flight package that will house our dart avionics. This will be below our parachutes and above the fins. And to finish off the dart, we're going to have our lower dart section, which will house our dart static fins and our air brakes and their electronics to control the air brakes. To start off the booster, at the tip of it, we will have our transition section, which will connect our dart to our booster, given that it has a varying diameter. And below that, we are going to have our booster electronics, avionics, that will control the deployment of our booster parachutes. And at the bottom, we will have our lower booster, which will consist of our motor and our airfoil fins. And we'll have a thrust plate at the bottom to transfer the forces into our body tubes. So on your left of the screen, you can see the general overview of how different stages of the rocket will occur. So we start with our ignition, which will take us to motor burnout. And at that point, our dart and our booster will separate so that the dart can achieve a higher apogee. While the dart's achieving apogee, our booster will have already achieved its own apogee, where its own parachutes will deploy as reefed parachutes. Further along that path, it will deploy its main closer to the ground, and then that booster will hit the ground. For the dart, as we approach apogee, we plan to deploy air brakes if we are exceeding our target apogee of 30,000 feet. And at that point, once we hit our apogee, we plan to deploy another reef parachute, which will then expand to main as we get closer to the ground. So here you can see our mass distribution of the rocket, and half of it is taken up by our motor. So it's a balancing act trying to maintain our stability with having enough weight to push our center of gravity higher than our center of pressure. So as you can see, there is also a lot of mass in our upper dart, and that's used to balance out where that center of gravity is. And I'll hand it off to airframe propulsion.
Hello, everyone. I am Andrzej Sterko, and I am airframe and propulsion lead. So today we will talk about air brakes, electronics, fins, and general airframe. And I will let Sierra start.
Hello, I'm Sierra Stockwell. Today I'll be presenting the air brakes. We also have some new members that will be working on us with the air brakes, but they're not quite ready to present yet, just for comfort. But we have Devansh Patel and Taryn Butler. First, we're going to go over our purpose, then design breakdown, prototype, timeline, and testing. Okay, so the purpose of our air brakes is to basically decrease our apogee to get it as close as possible. So we plan to overshoot, and then we bring our apogee down by releasing the air brakes at a select altitude that allows us to get as close as possible to that target apogee. The air brakes utilize both electrical and mechanical systems. The difference between this year and last year's air brakes is that instead of using a stepper motor, we're using a linear actuator. So instead of twisting to open, they will be pushed to open, which helps with a lot of the issues we had last year. The benefit of air brakes is that they could improve the team's apogee score and increase design points. Okay, so here's our design breakdown. The bulk of the air brakes will be CNC manufactured on the mill using multiple processes, and we plan to use soft jaws to be able to make both sides very accurate and clean. The material we'll be using is 6061 T6 aluminum, and these air brakes will be mounted below the motor tube that holds the fins in the dart. So there won't be a motor inside of it. there will actually be our linear actuator inside of it. And then the air brakes will slide up with the linear actuator and its mount up into the bottom of the rocket. And then the electronics that attach the linear actuator will mount above and attach into the top part of the linear actuator. We have added clearances between moving parts to avoid grinding, as that was a huge issue before, and tolerances will also be calculated before manufacturing. And we haven't begun CFD yet, but that is a huge part of this process. We will be starting soon. Our analysis season is beginning after this design review. So we will be testing if the air brakes make enough of a difference to justify having them, and if the wake after the fins is affected at all by the air brakes. And if you just click a few times, we'll get some descriptions. These are the blades, the arms that push down by the linear actuator, and then the connector. These arms are in two pieces so that we could get a greater angle to push the blades out more. If you click again, I think there's just the bottom bulkhead that all of the pieces connect to. And the top piece to keep them in place so they don't just slide off completely. Here is another design breakdown. This shows you the above image of the air brakes with the top pieces on, without the top pieces, and without the blades. So you can kind of see where my mind was while I was designing this. The slots around those holes there where the top slides into allow us to add clearance for the blades and keep the blades in place despite only having one hole to keep them there. And we also have slots that come from the inside out for the blades to slide on so that it stops them from sliding out too much if the linear actuator were to push too much. Next slide. And then here is an image of our prototype. We do have a little 3D printed prototype. This is where CAD vision kind of gets you because these air brakes are in the 3-inch section of our rocket. So you can see that they are very small compared to that quarter. And they do function the way that we planned, so that was a success. The only problem is that the arms aren't pushing them enough yet, so we just need to increase the size of the second arm that's attached there, and that should push them out more. So here's our timeline. You can see we had a preliminary design at the very beginning of our whole design season, and since then, we've had design adjustments and prototypes, and once we analyze, we will have another design adjustment based on any feedback from that analysis, and then we will begin to manufacture very soon out of metal, and then we will test it with the linear actuator and go into our last design adjustment based on that feedback from the electrical tests, and then go on to our final product before the test launch. Here's our testing. You can see that our 3D printed prototype testing did occur where we just tested the basic function of the prototype to see if we push down on it, will the blades all come out uniformly? And they did, but as I said, not to their maximum length yet. So we just need to increase the second arm's length. And linear actuator testing, we weren't able to complete yet due to the 3D printed prototype breaking a bit. So we've just got to reprint that little piece that the linear actuator attaches to, and then we will be able to test that soon. And then the metal prototype testing will happen sometime during manufacturing season before the test launch to test how the metal compares to the 3D print, since the 3D print experiences a lot more friction and we can't really lubricate it like we can with the metal part. So we will see how that turns out compared to the 3D print.
Hi, my name is Andrea Maldonado. I'm the electrical lead for MASA, and I will be talking about air brakes electrical today. Next slide. So the purpose of air brakes electrical is to actuate the air brakes so that they can get as close to 30,000 feet, so that the apogee of the rocket can get as close to 30,000 feet as possible. And the deliverables for our project is going to be data stored on an SD card that can later be analyzed after the flight. So design breakdown. The way the air brakes electrical is going to work is we're going to take velocity data using an IMU sensor and altitude data using a pressure sensor and inputting that data into a lookup table as well as the current position of the air brakes in order to output the next position for the air brakes. And doing that, and the way we're going to be doing that is using an STM32 Nucleo 32 board as well as two 7.4 volt lithium ion batteries. Because of the size constraints of the 3-inch tube, um, we are going to have to use SRAD boards to mount all our sensors and SD cards and stuff like that. So yeah, and um, aside from that, we also are going to we're going to derive an equation to find out what the proper linear actuator extension should be to get the proper extension for the air brakes plates. Next slide. So for the hardware block diagram, you can see that we have the lithium ion batteries that are going to go through an overcurrent protection circuit. And from there, we're going to use a 6-volt buck converter to actuate the linear actuator. And from the STM32, you can see that we have the SD card, the IMU, a buzzer, and a pressure sensor. For the software, we can start on the right for the main function. When we start, we're going to be reading the velocity and altitude. And as soon as the velocity reaches a threshold, when the rocket launches, we're going to start. We're going to start the timer, and at that point, we're going to find the data from the IMU sensor and from the pressure sensor. That to input that data into the lookup table and set the next position for the linear actuator. And on here it says 80.7 seconds. We're actually going to be doing somewhere around the ballpark of 840 seconds so that we give ourselves 14 minutes to complete the flight. And then after the flight completes, we stop the program. So schematic progress, we are 60% complete. There's very minor things that need to be completed, buzzer, fuse, battery connector, and we should be done with routing we should be beginning routing by the end of the month. Testing for the electronics, a big one is going to be integrating our electronics with the mechanical air brakes and seeing that we have enough force to what's the word? To extend the air brakes properly. We are also going to test the accuracy of the lookup table through the I'm so sorry, I'm getting nervous. Through the practice flight that we're going to be doing in March. And after that, we also are going to test the geometric equation outputs. At the same time, they're going to be integrating the electronics. Next slide. So our current budget, as you can see, the average current is going to last us 5.5 hours. At max current, we're going to be lasting 2 hours. This isn't ideal, of course, but that's just using the batteries that we have in our high bay right now. It's just a matter of ordering batteries with a higher milliamp hour thing. Yeah.
Hello, I'm Sarah Dormal, and I'll be presenting the fins with Maxim. So we'll be going over the purpose, the design of the fins, FinCAD, FinFlutter, timeline, and a little bit of testing that we plan to do. Next slide, please. All right, so the purpose of the fins is to reduce force of roll and to minimizing the airflow diverging from the rocket, provide some stable flight. There will be two sets of static fins on the Dart and the booster. They will both have a biconvex airfoil cross-section and a trapezoidal shape. The fins will provide a more stable flight, which will be really beneficial to the cameras, the recovery, the apogee determining systems, because recovery is not going to deploy properly if the rocket is doing somersaults in the air. On the right here, we have the shape of a biconvex airfoil, and on the bottom, we just have the Dart fins attached to the CAD just to see what they look like. Next slide. Maxim.
It looks like his microphone isn't working.
No, we cannot hear you. Well, we'll see if you can get that working in just a second.
Hello.
There you go.
Hi, I'm Maxim Rushko. Sorry about that. So this is our design breakdown. Here you can see we have both CAD renders of both the booster fin and the Dart. We included a 1/2-inch tab on both fins so they could attach to the wall of the inner tube. That will help for mounting purposes. And to help achieve our 30,000 foot apogee, we had Open Rocket determine our dimensions, and they can be seen below in the chart. That will help with maintaining stability and minimizing drag. Top picture is a top-down view of the airfoil, and then you can see how the fins will look once they're attached to both the Dart and the booster.
So this is just a little bit of a breakdown of our fin flutter. The numbers that we calculated are using a theoretical shear modulus. We do plan to experimentally determine it once we get a nice specimen and we can take it to the lab. We use the equations shown on the right. And so what we know is that our fin flutter that we obtain from using the equations on the right needs to be greater than our maximum velocity, which is 1915 feet per second. And so our Dart fins right now have about a factor of safety of 9, meaning that the fin flutter that we obtained is about 9 times greater than our maximum velocity, and our booster factor of safety has about a 2.5. Next slide, please. So this is just a slide on our fin manufacturing. We've successfully made a fin prototype. We used 2 halves of a 3 printed female mold, and we made sure that these can be reused for all sets of fins. The fins are a carbon fiber epoxy resin, and they're a laminate, and they are not hollow, so it's just a bunch of layers of epoxy and carbon fiber. There are about 30 layers, and each layer is rotated on a 90, 45, 90 with an epoxy in between. The 2 halves are then clamped together, and it is left to cure. No heat, no pressure required. And the fin tab is built into the mold. And on the right, the upper right, we have a picture of the manufacturing where we're layering the carbon fiber and the epoxy. And then we have on the left a finished fin. Next slide. This is just a picture of our fin prototype. On the very left there, we have a head-on view. It's very thin and it's a bit difficult to see in this picture, but you can see the very nice pointed edge and the rounded top. And then we have our side view, which is our trapezoidal side, and you can see there are a few imperfections on it, but overall, I'd say it's a very, very good first prototype. And then we have an angled view there on the last. Next slide. Just a bit of a thin timeline. Our design season, we're well into that, and we're well into prototyping. We'll be beginning our analysis of CFD and like more deep in open rocket and simulations. After that is done, we'll be doing some redesigning, going up to about November, and then we'll start manufacturing. And manufacturing will continue until our test launch date of about March 11th. And then we'll go to final manufacturing, final touch-ups, final integration, fixing anything that broke until competition. Next slide. So it's testing. So we plan to test some manufacturing methods on how to make the airfoil shape, because that's been a big question in the past. Our expected result was that the fin would have the desired airfoil shape and wouldn't collapse in on itself or any sort of weird, funky things that happen. And that's what happened. The actual results, the fin had the desired airfoil shape, except for a few bubbles and a little bit of a divot on the top. And that happened about a week ago and was completed about the day after. We plan to experimentally determine the shear modulus so that we can get a more accurate number on our fin flutter analysis. We expect that the specimen will break, and then we'll be able to determine that number. We expect that to happen at some point in November. And then, of course, we have our test launch when the fins will be attached to the rocket. Hopefully, they'll have minimum wear and they will not have broken off, according to our fin flutter. Our scheduled completion for that is, of course, the test launch, which is March 11th. Next slide.
Hi, everyone. My name is Caleb Peterson. I'll be going over the purpose, design, breakdown, transition, and then Audrey will go over the open rocket and propulsion. So our purpose for the general airframe is to provide a stable support for all the systems in the rocket, both structurally and aerodynamically. Next slide. For the design breakdown, the airframe consists of COTS Van Karman nose cone with the body and coupler tubes being also COTS G12 fiberglass. There will be a transition between the dart and the booster, which will go from a 3-inch dart to a 5-inch booster, as we heard before. The dart will separate due to drag naturally when the motor burns out. The total length of the rocket will be 12 feet 9 inches. So, as mentioned earlier, the transition will provide a aerodynamic transition from both parts of the rocket. It will also be made out of COTS G12 fiberglass, just like the rest. Next slide. And here is the general airframe diagram. It's an exploded view of the main rocket. We got the nose cone, upper dart, flight package, lower dart, transition, upper booster, coupler, and lower booster.
So hello everyone again, and we did do a lot of simulation with Open Rocket, and here is just our model in Open Rocket. You can see on the top the full rocket and then a dart on the bottom, and you can see center of gravity and center of pressure. Yeah, next slide. So some broad analysis. These are really rough right now since our systems are still being developed. So it's a living, breathing thing until all of the systems are fully developed. And so right now our apogee is 30,400 feet. That's without air brakes, and then flight time is 298 seconds, which is about 5 minutes, and acceleration and on a right is a graph that shows separation of a dart and a booster. Uh, yeah, and the important thing of here, our max velocity, we're going almost 2 Mach, which is a challenge for us too. Yeah, next slide. So stability analysis. So we have a competition requires us to have minimum of 1.5 stability to 6, and so our stability for the whole rocket before it separates is 237 calibers, and then when it separates, the stability of a dart is 285 calibers, and here are the graphs on the right that show the separation and stability. Okay, next slide. So here I will just go over our motor choice. So we had another option with N5800 motor, but the problem we figured out when we did some simulations that it's fast burning and our acceleration would go to about 22 Gs, which would cause a lot of stress on the system. So we chose slower burning motor, all 3400, which is similar apogee, and our acceleration went down to 14.8 Gs. Yeah. So our general airframe timeline, we plan to finish the whole rocket before test launch, and there are a lot of design adjustments that we will do because systems are being developed. And then after the launch, if we have to, we might even need to rebuild the rocket. So we did already purchase 2 sets of tubes and everything for 2 rockets in case we need to rebuild it later. Yeah. Next slide. And for testing, one real way to test our rocket is to actually fly or in a wind tunnel. Since we don't have wind access to wind tunnel, supersonic wind tunnels, we will have to do a test launch, and we will do a test launch in March in Muskegon using M34 motor. And we chose this motor because it gives us similar stresses on the rocket, and it goes to only 10,000 feet, which lets us launch in Muskegon. Yeah, thank you.
Hello, everyone. I'm Jamal Kazada, and I'll be doing the parachute systems for recovery. And then below are all the other people in recovery that'll do the next other slides. All right, next slide. All right, so parachute systems. Next slide. All right, so for parachutes, they will be student researched and developed. And following the successful recovery from last year, we'll have the same style parachute, which is 50% hemispherical reefed. So the way we reef is we use tender descenders, which are pictured in orange over here. So they're a type of link release or line release system that is activated with black powder, a black powder signal. So it's wired on the right. You can see the constricted view of the parachute. That's going to function as our drogue. And then once we get to a certain altitude, the tender descenders will receive a signal, and only one of them needs to release in order for the full parachute to open up. But both of them are built in for redundancy. So below we can see our descent rates and our projected our preliminary diameters for the main and the drogue. And then on the right is our snatch force range, which is from 300 to 1,000. Something new that we'll have this year is we're going to add a slider for better shroud line management to prevent tangling during descent. Yeah, next slide. All right. So for shock cords and hardware, we have our diagram over here with the shock cords sized at 3 times the length of the vehicle they're carrying. And for shock cords, we're going to attach them to quick links for easier installing. And they'll, instead of knots, they'll have this box stitch pattern on them, which should be rated for however much the vehicle will experience. And then to signal the tender descenders and the parachutes, we have on the right is the kind of wiring diagram of how they'll be put together. And these will happen in the purple sections of the shock cord diagram. They'll go from the avionics bays to the parachutes. Yeah. And then below are the safety factors for both snatch force estimates. Yeah, next slide. All right, so something new we're doing is we're going to have a smoke system to see the booster descend and as a proof of concept for later years. It's going to use an electronic-based smoke emitter, and it's going to be cool burning, so no risk of melting anything around it. And it'll be mounted into the booster avionics bay. All right, next slide. All right, for our timeline, we have design season, then we get the preliminary values, which is where we're at right now. And then once everyone gets their masses locked in, we'll obtain final values and start manufacturing for the test launch in March 11th. And then if there's any changes that we need to do, we'll readjust them and possibly remanufacture or make edits to the parachute. Yep, next slide. For testing, we're going to use OS calculator to get better snatch force predictions, and that's going to be around February of next year. All right, now on to ejection systems.
Hello, my name is Laretha McDonald. I'm doing the ejection systems. Yeah. So for the ejection systems, we use the F4 black powder oh my gosh, I'm so sorry. Black powder as pyrogen in the burrito charges. And the burrito charges are on the right side. There's a little diagram of it. And we estimate the size using the ideal gas law, and we will ejection test to confirm that our calculations are correct. This year, we will use Phoenix connectors to make integration across bulkheads easier, and we will practice assembling burritos with sand to get ready for launches. And at the bottom, it's really our calculations for the number of shear pins, the pyrogen amount, the amount of grams we'll need of the black powder, and the PSI ranges for the burrito charges, or not the burrito charges, but for our ejection system. Next slide, please. Thank you. Right now, we are updating the values, seeing if there's any corrections that need to be made to the calculations or anything. And we're kind of going into the manufacturing and testing and somewhat the ejection testing before the test launch. And we'll adjust the values around March 20th to May 1st if anything needs to be changed for the main launch in June. And there will be a possible second ejection test early May. And right now we will be testing if all the systems with a significant mass into the rocket and test to verify the calculations. And we expect that the separation occurs with no damage to the systems. And the scheduled completion will be around February or March of 2023, and the actual completion is to be determined.
Hello, hello. My name is Jidechku Owo. And I will be presenting alongside Temitayo for the Dart Avionics Bay. Next slide. All right, so the purpose is for the Dart Avionics Bay is to house the Dart Recovery electronics. It will be 3D printed out of PETG, and as you see below is the current prototype. And to the right are the safety switches, which are at the top. If you can just click, yeah, the safety switches, the RRC3 altimeters, and the battery mount for the 9-volt battery. Next slide. Okay, so for our design breakdown, we will have 3 pressure holes drilled with a 44 drill bit, and below are the system interactions. So basically, as an overview, the green arrow represents the mounting relationship, and then the blue arrows represent the signaling interactions, and the red ones are the forces. And to the right is the corresponding safety factor to each snatch force. And as you see in the diagram, the switch hole size is 1/4 of an inch. Next slide.
Hi, my name is Temitayo. So here we have the design, the block diagrams for the Dart Avionics Bay. So we're gonna get power from the 9-volt battery. It's gonna go to the switch, then the RRC, and the blue drogue signals are for the ejection, while the orange signals are for disreefing the parachute. And the altimeters are redundant. So yeah, I just want to point that out. Next slide. Yeah.
Hello everyone, my name is Bruna, and I'll be presenting about the Booster Avionics Bay. So the Booster Avionics Bay is responsible for housing the electronics, such as RC, safety switches, batteries, and the tele GPS. Oh, sorry. Okay. The avionics bay will be print of PAGG, and that's the currently prototype. Next, please. Sorry. Okay, so for design breakdown, we have 3 pressure holes drilled with a 27 drill, and the system interactions, it's for the BAB. Forces are in red, physical mounting green, and signals in blue. On the right, we have the exploded view of the BAB and safest factors on the iBoats. Next, please.
So I'm back again. This is the block diagram for the booster avionics. It's still kind of the same thing. We have power from the 9-volt battery going to the switch, then to the altimeters. The blue signals are going to the drogue signal. The blue drogue signals are for ejection. The orange signals are for disreefing the parachute. The only difference is that the aux signal is going to the smoke system, and again, the altimeters are redundant. So, yeah.
For the avionics bay timeline, we are currently in design season until the end of this month, and then we're gonna prototype during September through November. November to January 1st, we're gonna redesign manufacturing through January 15 and to March 20. March 20 to March 1st, manufacturing and the final integration will be occurring in May 1st through January 27. Next, please. Thank you. For the testing, we're gonna be doing two types of tests. For the drop testing, we're gonna find out how much force they can withstand, and for the altimeters, we're gonna use a vacuum chamber. The schedule we're gonna be test is gonna be occurring during this December 2002. Next. Thank you.
Okay, everybody, we're gonna have a 5-minute intermission. Just get up and stretch, use the restroom if you need to. We can get back here around 6:25. That's all right with everyone. Okay, seems like it's about that time. Next, we'll be going on to payload.
Hi, I'm Hunter Pruitt. I'm the payload lead this year. I'll be going over the payload mechanical along with Caden and Regina. Next slide. So this is this year's payload breakdown. We have the switches on the bottom along with the camera mount. In the middle, we have the experiment mount. On the top, we have the battery mount, and then the tele-GPS is mounted on the very top of the ballast. Next slide. So the purpose of the payload is to house the main electrical components, such as the GPS tracking device, the tele-GPS, and the experiment, which is the strain gauge and the raw data board, along with video capture. We chose a von Karman geometry this year to help with the 3-inch diameter that we were given for the dart. It'll allow us for maximum mounting space, and the mass is around 8.3 pounds. Next slide. For manufacturing, for the upper section, we're going to be having it's going to be housing the batteries, and for the lower section, it'll house the experiment board and the camera. The ribs and the bulkheads will be manufactured out of A36 steel, and we'll be using the CNC to manufacture the bulkheads and the ribs. The upper and lower sections will be attached with 1/4-inch steel bolts, and wire ways will be added for the strain gauge. And we'll be using 2 440 machine screws for each bulkhead to rib connection to allow rigid connections, and it'll prevent pivoting.
So our new payload members have designed and have begun prototyping the different mount designs. As you can see here, we have the designs for the camera mount, the tele-GPS mount, the experiment board mount or SRAD mount, and the battery mount. PETG has a higher glass transition temperature, and therefore we are going to be using that as our filament to 3D print the mounts, and we are using heat set inserts for reassembly. And as I said before, all the mounts have been designed and are in their prototype phase, and the heat set inserts are being included for a rigid connection to the bulkhead since we found that to be the most stable, and we are test fitting the electrical components and changing the designs as need be.
Hi, my name is Caden. So our experiment overview is a strain gauge on the body tube to measure the body tube strain as the dart is in flight. This is going to collect data that allows us to calculate and better understand the stress and forces the body tube will experience going to 30K. First time to 30K, so this data is valuable for future rocket designs and future teams to have reference when designing. We will do this by putting 2 strain gauges perpendicular to each other on the payload body tube. 1 strain gauge to measure axial strain and 1 strain gauge to measure transverse strain. Poisson ratio will relate transverse to axial strain. The use of both gauges in half-bridge configuration will cancel out thermal strain. The jig will be used to install gauges and wireways manufactured into bulkheads to ensure safe integration.
So we just finished up the initial design season, and we've moved into the prototype and initial integration. After the initial integration of the electrical components, we'll be moving into redesign, and then around the new year, we would begin manufacturing the main frame and testing the frame. And then after testing, we want to remanufacture, and then around May, move into final integration. Next slide. For testing, we want to run a mount and frame shock testing so that there's no fractures or warping between the bulkheads and the ribs. We also run a camera vibration test so we can discover different dampening methods so we can have better video quality. And we also want to run a battery life test so that we can ensure that the batteries operate at the expected amount of time.
All right, hello. I'm Sam Medalio, and will be presenting. Andrew Pearson and Rejwan Haq will be presenting with me for the payload electrical, and for the payload electrical, we'll be going over to GPS and the dashboard and the cameras and the onboard experiment.
Hi, I'm Andrew Pearson. I will be presenting the tele-GPS to you today. On to the next slide. The purpose of the GPS is to locate and recover the rocket upon touchdown. There will be one tele-GPS in the BAV and another one in the nose cone to locate the dart and booster. The tele-GPS is an independent system. It doesn't need anything else to run. On to the next slide. We will be using a COTS Altium Metrum GPS powered by two 3.7 volt lithium-ion batteries in parallel. The tele-GPS will use a whip antenna to transmit data at 900 millihertz. This may change to 400 once we have some hand certifications. I know a few of us are looking to take that test here pretty soon. So we'll see how it goes, and hopefully that will be the case. Data from the tele-GPS is stored locally on the rocket and locally on a ground station on a computer with a hard drive onto I believe the hardware block diagram. All right, so the tele-GPS takes in power from two 3.7 lithium ion batteries. Then it transmits to the antenna, which sends the information to the ground station. That's how that'll work. And then do we have a software block diagram? No, we do not. All right. So the testing, we will have 3 different tests. The first one is the distance test. The tele-GPS will give reliable data regardless of the distance between the ground station and the GPS. That's the expected result. We haven't quite tested that one yet, but the scheduled completion for that will be on November 10th. The battery life testing, we want it to last over 4 hours constantly on, because you never know when you're going to get going, and you can't really go in the rocket and connect and disconnect the battery over and over again. So we want that to last for over 4 hours. The actual results to be determined, and that'll be on the same date. The last test we will be doing for that one is the GPS's signal at various orientations mounted with the bulkhead. The metal bulkhead will have little to no RF interface with the GPS. We just want to make sure that it'll send a proper reading through all of that, and that'll be in January of 2023.
And now I will present the experiment slides along with Aaron. Next slide, please. So, as mentioned earlier in the presentation, the purpose of the experiment is to gather valuable flight data for the rocket. This includes temperature, current, altitude, and a bunch of other sensors, velocity, body tube strain. So, and this data will be stored locally to an SD card on board the rocket, as well as to the dashboard, which will be on the ground. Next slide. So we will be using an STM32 Nucleo, which will be powered by two 7.4 volt 1250 milliamp hour lithium ion batteries. And the Nucleo will be collecting data from the sensors, as mentioned earlier, and it will be storing it in an SD card and transmitting it to ground using an XB transceiver. And the experiment will be will be sending out this data every 20 milliseconds. Next slide, please. And Aaron will present the hardware block diagrams.
All right. So if you look here, seems we're getting information from the sensors within the rocket, in which it will go up to an XB transceiver, in which from that it'll transmit it to the dashboard down at ground. And that's how we will get the data. And you look at the bottom, 7.4 volt lithium ion battery powers the battery connector, which can then go to the 3v3 buck converter and a 5V buck converter. These battery connectors also power the current sensor, and which data will be sent to the Nucleo. Next slide. And when it comes to the software,
oh,
if you want to
sorry.
take this now?
Yeah. So for the software block diagrams, it's pretty straightforward. So we'll be collecting data from all the sensors in the experiment board, and the Nucleo will be reading those data, and then it will store in an SD card, and it will also send it out to transmit to ground. Next slide, please. Schematic progress. So far, it's 85% complete. We're just missing battery connector, fuse, and we need a current and voltage protection circuit for the Nucleo, a buzzer, and a couple resistor values. And routing will begin very soon once we've touched up on the schematics. Next slide, please. So for the strain gauges, we'll be using a shielded wire to prevent noise, and a half-bridge Wheatstone Type 1, and an op-amp to amplify the strain gauge signal. So we can, as you see, we have the schematics on the right and at the bottom. Next slide, please. And Aaron can present the testing slides.
All right. When it comes to testing, we have battery testing, which will test voltage, current, and power delivered to all components on the board. Our expected result is that the battery will last a minimum of 4 hours with components. The actual results are to be decided, and we plan to have scheduled completion anywhere between December or January 2022 to 23. Next, we have sensor calibration, which tests the accuracy of data collection, in which we expect that the data values from sensors match the conditions measured using other devices. We haven't yet tested this, so the results to be decided, but we will also test this between December and January of this year. Lastly, the transceiver calibration tests connectivities between transceivers, which transceivers between the rocket and ground will have constant communication regardless of distance or payload orientation. This will be tested on November 22 to 23, and the results are to be decided.
And here's our current budget for the experiment board. So we have our Nucleo at the top, with our average current being 450 milliamps, making up most of the current draw for the batteries. And we have a max current for 800 milliamps for the Nucleo. And we have a bunch of average and max current values for the other sensors and the SD card. And here's our total current for the average and max currents. And we are expecting our battery life to last at an average of 5.5 hours, and at the and no shorter than 2.44 hours. Now, next slide.
Hey, it's me again. I'll be presenting the dashboard to you guys. The purpose of the dashboard is the ground station on a laptop will receive flight data from the rocket to log and graphically display the data for members to view in real time. There will also be an option to view the exact data in spreadsheets as it's updating. This is the startup screen that you guys will see when you open the application. The dashboard will have docking and undocking capabilities to allow more important graphs and tables to be expanded. This will be helpful, especially during testing, if you want to test specific aspects or if you want to look at specific graphs more carefully than others. We will use an STM L412KB nuclear 32 powered connected to the ground station. An XB S3B Pro with an antenna will receive data from the payload. Onto the next slide. The system will output the following data from the ground station. It'll output the current the temperature, the altitude, pressure, body tube strain, velocity, accelerate, roll, pitch, and yaw of the rocket, and the GPS data, which will probably also have a map that goes along with that. This is on the right, you can see kind of a sample diagram. There's a few of the graphs that are missing, but those will be added. That's just a sample for how it's going to look. There'll be more extensive graphical data when we actually develop the dashboard. The output rate will be 20 milliseconds per sample. The data will be stored locally on a hard drive on the ground station. Both data tables and graphs will be displayed, although you will be able to turn those off and just view the graphs or just view the data tables as you need. That'll be an option or a feature that we develop. It's not a super necessary one. It could just we could just have the data tables and the graphs being displayed, but it'd definitely be a nice feature to have. I believe. Yep. So this is the hardware block diagram. So an XB transceiver will transmit to the ground station. The STM32 will take in that information. The dashboard will take the information from there, convert it and display it, and then the ground station will store it. The STM32 will be powered by two 3.4 volt LiPo batteries converted down to 5 volts so it doesn't shut off. I think you can go onto the software diagram now. So it's a little bit of a complex diagram, but just to give you a rundown, if you start in the top left, you can start a new project, open an existing project, and then it'll take you through the creation process where you can give your project a name and save it to a local file. You can then start the flight. It'll look for the signal from the STM32 and go through. If it's not received, it'll display it. It'll try a few times and then it'll display an error to show you nothing's connected. At that point, you can determine what to do from there. If it is received, it moves down to the data is graphically displayed. It'll always display flight data regardless of if it's empty or not. It'll just display a graph that shows 0 along the y-axis and a positive time flow. And then you'll be able to see those graphs in real time. And then moving on to the post-flight data, you push the end flight button. The data is saved, and then you can either reset the flight, in which case you can save, or you can just delete the data depending on what you're trying to do. If it's just tests, you might want to delete the data without saving a bunch of clutter. Or you could just exit, or you can start a new program or open an existing one. All of these options will ask you to save, because during competition, it'd be quite unfortunate if you lost all of your data because you didn't. And I believe that's all there is to that.
Hello, my name is Mo, and I'm going to be presenting with Chance Ashworth.
Hello.
We're going to be doing and talking about the camera system. So the purpose of the camera system is going to be to record the flight and basically store footage just so we can watch it back and actually analyze the flight for future promotional material. The camera will be located at the bottom of the rocket, as I believe it will be at the bottom of the payload. It will be using a Raspberry Pi 3A, which will be powered by a 5,000 milliamp Pi Sugar battery, and the video will be stored locally onto the Pi's micro SD card. The camera will record up to 1080p at 60 frames per second. And here we can see the hardware block diagram. It's a pretty simple one. It's just going to be the Raspberry Pi 3A, which is connected to a 5,000 milliamp Pi Sugar and the Pi camera as well.
And as for the software, it will start, create a directory to store new files in. It will start recording, and after 30 seconds, it will start a recording, as long as there's room on the SD card.
Hello. Okay. So this is our payload electrical timeline. So as of now, we are currently in our routing, prototype electronics, and dashboard development stage. Although this may be subject to change as it may take some time to finish up our schematics. And we plan to start to order our PCBs around November. And we're going to start programming our payload electronics around October 25th through January 1st. And from January 1st to February 1st, we plan on soldering all of our schematics and boards. And from February 1st to March 10th, we will be doing testing and troubleshooting for all of our electronics.
Okay, John and I will be going through the risk analysis. We'll just be going through some highlights. So you can see here is our matrix, probability in the X direction, impact in the Y. And this overall just relates to, it's a multiplier into the overall severity. So that's just color coded. So orange in the top right is high severity, green top in the bottom left, low severity. You can see here, if you want to review to your slides that we sent to you as well later on, feel free. I'll just be going through some of the payload risks, and then John will go through airframe and recovery. So the switches are an important part of the rocket. And so we have found that sometimes you can get sand or dirt that enter the switch. So what we need to do is verify through our test flight that we will be able to actuate the switches correctly. And then if we run into any issues with that, we may come up to mitigate it. We may come with some solutions, such as not necessarily pressurized air, but something along those lines where we can clear out any dust or dirt that interferes with it. Along with that, the electrical for the tele-GPS, we really need good signals without any faulty data points. So we want to test interference with the bulkheads. So our test flight will be a really good test for that. But before, we want to have our tele-GPS on a mount under a nose cone, and we want to see the range for how far until we receive faulty data or none at all.
So for our recovery electronics, our first potential failure is our Dart and booster avionics. So if we don't have our avionics working properly, we won't be able to record our flight altitude and deploy our parachutes. So it's going to have a major impact, and we are going to go through various testing to make sure that we can reliably have our avionics. Another big potential failure mode that we're trying to remove is tangled parachutes on ejection. And to mitigate that, we are going to double check, triple check that our parachutes and is packed correctly so that we do not get tangling. Because if that happens, then we might not even recover a rocket. So. Next one is our main deploying at apogee. The biggest downside of that is we will have to go a long way to recover a rocket, and at that point we might not be able to get data from GPS. So we need to make sure that we have our reef parachute deployed at apogee and our main deploy closer to ground, and we are going to again triple check our systems, including the reefing line and our hardware on the parachutes. Going on to airframe now, our first major failure mode is that our fins break off during flight. At that point, we have no say where the rocket's even going to go, and it's definitely going to fail. So we are going to emphasize the structural mounting of our fins through wall onto our motor tube. with fiberglassing, so that we don't encounter those kinds of failures. And we are also going to use a fin jig during this process to make sure that our fins are properly aligned and we do not have spiraling flight. So our next one would be the failures due to air brakes. So if the blades end up moving by themselves and not as the linear actuator and our testing would suggest, then we would have uncontrolled flight when we get closer, when the air brakes deploy at an unopportune time. So we plan to use limit switch to make sure that we do not have any incorrect deployment of our air brakes. And then now on to the general airframe failure modes. The biggest one is that we do not actually have separation during our flight, and we're going to test that during our test flight, and we're also going to analyze the friction between coupler and lower dart, so that we can make sure that and do force analysis to make sure that we do not have the coupler of the transition sticking to our upper dart. Devin, your mic's muted.
Yeah, so we'll be going on to project management here. John, would you like to talk about the mechanical design completion?
Oh, yeah, sorry, my bad.
No, you're good.
We have made a lot of progress on our mechanical designs, and as you can see, a lot of our sub-teams have already progressed into prototyping and analysis. The main points we need to keep working on are payload mounts, continue making sure that those get go through testing on those and make sure that those designs get completed properly. And we still have some work to do with our strain gauge experiment, making sure that everything's mounted in a way that it's possible to integrate. And going on to air brakes, we still have work to do on our air brake electronics mounting and making sure that those systems integrate with our electronics. Other than that, we've made a lot of progress in the other areas, and we're continuing on to our testing and manufacturing.
Hi, so for the electrical design completion, as you can see, we still have quite a bit left to finish, but if you bear in mind that a lot of our members this year are new members, we've been spending a lot of time right now just training new members, getting them up to speed with the knowledge base. So we're at a pretty good place right now with training members, and once we finish that, we'll get more work done. But yeah, we still need, for the SRAD hardware, we still have to finish the schematics, we have to do routing, and we have to solder after the fact. Board programming, we haven't done a whole lot of progress on that. We're still training members on programming the STM32s. For dashboard software, again, we're still teaching members how to, do programming for that as well. As well as the hardware. Tele-GPS, we're almost done with that. We've been having some issues getting the software to work. We think it might be an issue with the batteries, actually. But yeah, so we're almost done with those. And software air brakes, we've been doing a lot of research and lookup tables, but we still need to program the actual hardware. And air brakes hardware, we have a good chunk of it done. Again, just finishing schematics, routing. After that, the avionics base doesn't take a whole lot of time to finish. So we're almost done with those. Yeah, about 40% done with progress.
Okay, great, thanks, Andrea. And also bear in mind, a large portion of our manufacturing season will be mitigated for by having these COTS boards. So the front end design season should be a little bit longer, and that will account for the shorter manufacturing season as well. So with that, we'll be going through the financials. Here's our budget justification for our budget, along with funding sources and sponsors. So this will round out the presentation. So you can see here our budget comparison from last year to this year, just an increase of around 6,000. And there's an admin budget up here that you can see. I will break down later. The airframe and propulsion, payload mechanical, and recovery sub teams have absorbed the electrical budgets, just with some restructuring of the teams, but it makes no difference for the overall total budget. Mechanical and electrical general, this is for new tools, things that are necessary to make the teams actually function. So we'll break down the admin budget a little bit. A large portion of it actually is lodging and travel. And then L1 certification class is under this admin budget as well. And then finally, 9 and then 6% are for competition fees and marketing and apparel. And then some other key reasons for the increase, reliable and standardized rocket kits to improve certification class success rates. These kits can also be used for L2, so it helps us save a little bit of money further down the line. And then the test launch also requires new motors and backup components, so that's a new expense that we have to deal with. We didn't have a test launch last time, and we didn't use a motor, so if we have any backup components that we need to be purchased, we will. Along with that, purchasing necessary tools and tooling, like I said, this will be for our general electrical and mechanical budgets. So here's our funding sources. We've requested 30,000 from CCS. We are soon to be hearing from them about the status of that. 20,000 from the Woods Foundation, Ford Motor Company 5,000, Giving Blue Day 2,000, Magna is 2,000, and Kalita Air 1,000. So totaling in $60,000. And then here's a thank you to our sponsors for supporting us. And last but not least, thank you for joining us. We would like to start with questions and a final discussion. So if this works with everyone else, I think we can just start from the top alphabetically. So I can start with Barnabas. Do you have any input or anything that you would like to say?
Sure. Hello, everyone. On slide 51, I saw that you guys say the dart will separate naturally.
Yes.
Due to drag on the booster after motor burnout. Is this something that other teams are doing too? Is this I guess, a method that has some, I guess, real world testing, or it is something new?
Yeah, and we've talked with Rob about this actually. A boosted dart configuration. This is kind of it's been run before in this configuration with a limited diameter. That allows for less drag on the dart and more on the booster.
So the separation is not actuated, but is actually only due to the drag of the.
Yeah, exactly.
Okay. All right. And then the other thing is, has there any CFD been done on the air brakes so far?
Yeah, I can actually, John, if you want to talk about this. John, Jamal, and I are actually in Pescaro's CFD class right now, so we'll be getting into that soon. Yeah. So he talked about you.
Yeah, so we're planning on we're in the CFD class, so we're still learning. We're getting into ANSYS now, and we're hoping to model air brakes and other systems on the rocket as we go forward. We're at the point where we're learning how to use the software, so we hope to be able to accurately model them. I know you had that experience, and if there's anything you can add, that would be helpful.
Sure. I think I have a file set up that after a very long amount of trial and error worked. I can send that over if you guys want. But obviously, a lot of things will have to be modified, like the velocity, the geometry of the rocket, etc. But
yeah,
that's really useful.
That'd be really helpful.
That'd be great. Yeah, thank you.
All right. Sure. Sure. If I were to forget, just remind me. But it should be good. But yeah, sound great PDR, great PDR. So sounds you guys get a lot of things done that we got done way later when I was on the team. So
Thank you. I appreciate it.
all right, and those are all my questions.
Well, thank you. All right, Dr. S, do you have any input or any questions?
No, not this time.
All right, great. Also, just a reminder, don't forget to fill out that the rubric. That really helps us with grading, and it shows the university our progress. While I just remember, let me look through the list. Professor Khosravi, do you have any input or questions?
Well, unfortunately, I had prior commitments. I joined in fairly late.
No worries.
I don't have any question, but if you could share your slide deck with me, I would really appreciate it, and perhaps I could get back to you after having had a chance to review it.
Yes, of course. Yeah, I'll make sure to resend that.
Thank you so much.
Yeah, no problem. Lucas, I'm guessing you have some questions or comments, I'm guessing.
Yeah, me, Matt, and Josh and I all have a document, so I don't know if you just want us to go all together at the end or something.
That might be best. Yeah, that way it might be a little bit more time consuming. We can save everyone's time. That'd be great. Yeah. So thank you. All right. So Matt, Michael, do you have any questions? I saw you were in the chat. You had a couple questions.
Yeah, but probably more than I'd like to. That it'd be probably be better if I just put them together like in an email.
Great.
Yeah, I was gonna say, did Matt and the others warn you guys about me? Sounds like that's a yes.
No, thank you.
I
that would
guess
be great.
there is one quick question.
Yes.
On the strain gauge experiment.
Yeah.
Using just a simple op amp is really not going to cut it. You know what? It's probably better if I put this in an email. I'll bore everybody to death about this.
Okay. Well, thank you. And then Miguel, I don't know if you were tagging along with their document.
Oh no,
Yes.
I haven't talked to these other guys. I just have some thoughts of my own.
Okay.
They probably have some very valid independently thought of questions.
Yeah. Miguel, if you're speaking, I think you might be on mute or something. So I'll wait for you to get that sorted out. And then we go to Rob. Do you have any questions or input?
Yeah, quite a bit. Do you want me to go now or wait till the end?
Would you like to wait till the end? We can go through.
Yeah, that's fine.
Okay, great. Thank you. So, Stephen, do you have any input? And then Trent, how you doing?
Howdy. Yeah, I'll let Robert take the lead on this one. He's probably got more insight than me, but yeah, if you got some time, I got a few things.
Great. And then is there anyone else that has any input?
I'm with you, Devin. I got some input.
Okay, cool.
And then I'm here with Kyle as well. I'd say we could go at the end, but I think everyone else has already said.
Yeah, it seems like we're saving everyone for the end.
Yep. So I don't know. We can all just sort of go at the same time. If we've all got lists, we can just start at the top of the presentation and work our way down, if that works for folks.
Yeah, I think the most efficient way is just highlight through it and then send details in emails to us. That would probably be the best, if that works for you.
Okay. Yeah, I didn't know how much you wanted to discuss today. I just mean for anything you want to talk about today.
Yeah. Yeah, no, that's perfect.
Okay. Yeah, if you want to do that, my first thing's on slide 12. Talking about the body strain gauges, the experiment. I understand it's to get more accurate flight data. In the future, I'm just trying to think of what the most useful application of this would be. Or is the plan to move forward with custom airframe designs that may be stronger, such as filament wound carbon fiber or home brew body tubes out of fiberglass that are stronger than Wildman's, or where's the thought there?
Yeah, essentially, my thought behind it was, we don't really know exactly what compression we'll see in that material. I mean, I assume it will withstand it, but any like even oscillations in that compression, that would be something really interesting to see, because we never really monitored what kind of force we have on the rocket before. So other than I guess in the nose cone, my before my freshman year when we had the pressure sensor array.
Sure.
Yeah.
All right. I think my next thing was on the next slide, slide 13.
Yep.
Yeah, for the motors, I noticed the M3400 is a Caesar-only motor. I don't know if you guys have a case for that. So if you were looking to save some money, if you went with an Aerotech motor, I know that we have more cases. And cases will run a few $100, so it just saved you some money if you wanted to find something for a case that you already have. I don't think you have the Caesar-only 98 4-grain case, but correct me if I'm wrong.
No, I don't believe so.
And you may find that availability is going to be a problem for you as well. So if you don't need one, let me know and I will ask the high power community and we'll find you a loaner if you need one.
Oh, we would appreciate that. Yeah, thank you.
Yeah, I know we had a real hard time last time trying to get a Caesar-only case. It took about 8 months. So yeah.
Yeah, I remember that.
That'll be interesting. Next, I'm on slide 23.
Before you leave 13, Justin, can I step on your toes for 1 second?
Go right ahead.
On page 13, your last item, a reef parachute to save space. Reefing a parachute does not save any packing space. It makes the chute drop faster, and there's certainly advantages to that, but it doesn't save you any space reefing the chute.
Okay.
All right, before you go to 23, I got one at 22.
All right.
Or yeah, so your air brakes deployment, you're doing it directly at 30,000 feet, and you only have roughly 3.5 seconds for your total air brake phase. Is that even enough time to fully deploy your air brakes and get enough slowdown? Or
I can talk on that. So we're gonna do the CFD analysis going forward. So we don't really know how much of an effect it'll have just yet. So once we get a little bit more information, we can choose a better time to deploy our air brakes. So it's not really set in stone yet. It's just showing that it'll be close to apogee, close to 30,000 feet when we deploy it. So we still have some work to do to make sure that we deploy it at the optimum time.
all right. Yeah, I know when I did my control system, I had 6 to 7 seconds, and I found that I was only able to bleed like 100 feet in 6 seconds. So be prepared to need as much time as you can get.
Okay.
Yeah,
thank you.
This is actually where my comment was on too. I had the wrong slide number written down. But they should deploy, at least based on the previous methodology that we used, when booster separation occurs, so that you have the most amount of time.
Yep.
To have an effect on the flight, because if you deploy them at 30,000, your gain is going to be very minimal.
I see. Okay, thank you very much.
Yep. And then my next thing is on 36, if anyone's before me.
We have, I guess 27 is one that we got. All right. So one of the things I think you mentioned that there was clearance, a decent amount of clearance on the connectors. With the amount of clearance you guys are expecting, is there going to be any issue with, I'm a bit concerned about backlash. So if you have any like adjustments, like back and forth in your flight, you'll have to make sure you account for that backlash in your software, because you might not be where you think you're going to be if you do a lot of back and forth movements.
The clearance is very small. It's just to allow for easier sliding.
Okay. I would be aware, though, just try to make sure you can measure any backlash, just so you have a higher level of precision.
Okay.
All right. Anyone else before 36?
I got
34. Going on 34. Oh, yeah, we got 34 as well. You want to go there real quick?
All right.
All right. So long story short, please don't use 2 separate batteries and hook them together. That's just kind of asking for problems from the LiPos. If you need a bigger battery, just get one larger battery. And I, honest to God, don't think you actually need a bigger battery. And additionally, your stuff says that you want to use the onboard regulators on the Nucleo. That's a bad idea because those are all going to be linear regulators. So you're going to end up getting like 50% power efficiency on that. So just swapping to a buck converter module, you don't have to route or anything, just literally slap on the board and use, will save you a ton of battery life immediately if that was actually your plan.
Yes, to extend off of this, I actually have a comment, something slightly different. But when it comes to this, especially with the power situation, so the Nucleo boards, there's 3 reasons why the 7.4 volt thing's not going to work. One of them with Matt mentioning the power efficiency. So the Nucleo boards step down its VN input or its 7 to 12 volt input down to 5 volts with a linear regulator, and then it steps it down again with another linear regulator. So your efficiency is going to be absolutely terrible. And then I forgot the next point I was going to immediately say. I will remember to email and send the rest of it in the electrical meeting tomorrow. One thing that's going to be slightly annoying when if you guys do go the route of stepping it down to 3.3 volts, you won't be able to program it through the ST link as nicely. So you may want to set up something to either have a way to power it when it's not for the rocket, or basically just or you plug it in and program it through the J links that we have, which is just something to keep in mind, because when it's not powered at 7.4 volts, those Nucleo 32s do not activate the ST link. That should be it for my thing here on this slide. Actually, I guess I could put in one more thing here. So it seems like mechanical and electrical have, at least from the slides, it seems like mechanical and electrical have 2 different goals of how the air brakes plan to work. If the air brakes deploy at 30,000 feet, there's no point of running a lookup table. That is just send it fully 100% and then close it later.
I did not know that anyone was planning on deploying them at 30K. That was not my plan.
I
I
didn't put in a very accurate. I didn't put in an accurate amount because I wasn't sure what we could expect. So we just need to figure out what kind of drag we're going to have before figuring out when it's going to deploy. So
yeah, that's definitely something to do. It's just something to just think about. I know miscommunications happen and just stuff like that, but at least from how it's presented, that's just how it shows, even though I know that's not your guys' actual intent. But that's all I have for this slide.
Okay. Moving on. Do we have any other suggestions for the next slide?
38, I think, was one.
I'm on 36. I got you there, Lucas.
Got him beat.
Yeah, this one
your stuff also says 36.
Oh yeah, mine
Lucas.
was 36
too.
Oh, okay.
Then you've got the same thing as me. Go ahead.
So one of my main concerns is, first of all, calculating the velocity from the IMU. How do you plan on doing that? Is this going to just be an integral-based method, or?
We were planning on searching up a algorithm, just a basic equation online. We haven't gotten that far yet.
Okay, I would be very careful with anything that's just integrating or doing anything like that, because you can get a lot of drift. The complexity of something more is a lot harder, but I would be very careful with the approach you go with that. The drift can be pretty significant.
Right, but
and
you
then-
have no other choice if you have no other sensor to help aid.
Yeah.
Well,
You'd
I
have to
realize
do
if it's an IMU, it should have some other sensors on there, and a good one at least will have sensor fusion on board that you can pull more accurate data from.
Yeah, but I mean, that's based on using gyro measurements as well. And the thing is, those gyros only measure angular rates. They don't measure absolute orientation, which means you're going to need some sort of when the rocket's at rest, you're going to need some sort of like a alignment algorithm or such.
I think typically those also, I don't know about the ones they're using. A lot of them also come with magnetometers to try and get absolute orientation from the Earth's magnetic field as well.
The B&O, and Andrea, do you know if you guys are using the B&O 055 again?
I believe so. Yes.
So the BNO 055 does have some built-in sensor fusion, and for an orientation, you can look up. There's a gravity vector one that will give you a orientation relative to gravity, as well as there are some other pre-built ones. So if you look through the data sheet, there will be some. You can just set a few bits, and it will automatically turn on sensor fusion.
Right,
for you.
that's only going to give you 2 axes, though.
Yep.
You would need the magnetometer in order to get the third one.
I think there is a 3.
Yeah, the BNO has a magnetometer in it.
Oh, okay.
Yeah, no, I'm sure it's because I thought it was a 9-axis sensor.
Yeah,
so
it is.
Should have all 3 in it.
And then, are you doing any design of this control system in Simulink at all, or is this all just going to be?
We haven't thought about using Simulink, but we can. I'm not exactly sure what the what Simulink does.
So, Simulink would be, it's effectively just a visual way to design the control systems. It's what I ended up using for the design of this control system the previous years. One of the benefits being is you can automatically generate C code from it. So you can create all the things, all the blocks, and you don't have to manually implement like a PID system. Another benefit is it's got a built-in Kalman filter. I don't know if you will, ideally if you could use one, but you can get away probably without. But I ended up implementing one, and I was able to get the 2 combinations to get more accurate data.
So sorry, my computer died. I didn't get anything that you said.
So basically,
Yeah, we can get that in the recording.
Yeah,
Okay, yeah, no problem.
I would highly look into Simulink and just play around with that. At the very least, it'll help you in your courses later on.
For sure. Thank you so much.
Also, Andre, if you need something, I'm still in the high bay. If you just want to go over to me and talk to my computer.
I also am on Discord.
Okay.
All right, let's see. I have 39 written down if no one has anything else before that.
I have 39 as well.
I had one more 36.
Okay, long story short, these current numbers are not at all correct. STM32, they have a built-in power estimation tool. For the one that you're using, like the max you can get out of it is like 15 milliamps. So I don't know where you're getting your numbers from, but the STMs are way overinflated. And likewise, your sensors are way, way below what they should be. And I'm not sure about the linear actuator. It's probably going to depend on what actuator you actually end up using.
Okay, I'll look more into that. My bad.
Yeah, I think Lucas counted. The 450 milliamps might be if you have every I/O on, syncing the max current the chip can possibly sync through them, which is very unrealistic to put lightly.
I think those numbers are just the max ratings of the linear regulators on the.
Oh, that would also do it. Yeah.
I see. Not bad.
So yeah, I think all your current numbers are like that. They all need updating.
Will do. Thank you.
The issue that I wanted to discuss on this slide, and actually it's on several different slides, where you're talking about current budgets and battery testing and battery life and things like that. Keep in mind, because especially since a lot of your testing dates are in December and January in Michigan, you are not flying this rocket in December and January in Michigan. If you don't have every single component in an oven at 180 degrees, you have not successfully tested it, because that's the temperature range the thing's going to be operating under while it flies in the high desert in June. So just everybody who has any battery powered component that they are responsible for, you need to keep operating temperatures at the time of launch in mind when you're doing your testing and your capacity evaluations.
That 180 degrees Fahrenheit, I can't figure right off the top of my head. That's probably around, that's over 50, 60 degrees Celsius. Yeah, 50 degrees Celsius is 122. If you're using lithium-ion batteries, how well do those work under those temperatures?
Exactly. But 115 degrees atmosphere in incredibly bright, powerful sunlight inside a dark colored fiberglass tube, you will pass 150 degrees inside that tube pretty quickly.
Okay, yeah, we chose lithium ion just because that's what we'd been using in the previous years, and that's what we had in stock. But
oh, sure, no, I wasn't questioning your choice.
No,
just making sure when you test, make sure you're keeping the environment in mind.
For sure.
Yeah, thanks, Rob. yeah, that's always a good point. You always got to think about the environment too.
I'm at 41 if no one's before me. Okay, a couple things. First one was fin jig. I assume that we're going to use a fin jig to get those fins straight. Are you just going to use a similar design to what you've used in the past? I think Sarah made it in the past.
Yeah, so we'll be using a similar design to what we used in the past. Yeah, especially we can even create like a fin jig to kind of be a bit more accurate to the shape of the fins that we end up making. But yeah, we'll be using a fin jig.
Right, and I figured it might have to have a bit of a curve into it, because if you've got that flat, just flat, it might cock it a little bit. And then my other question, I guess, is technically not on this slide, but it's: are you guys going to use a thrust plate on the booster?
Yes.
Yeah.
All right, I just didn't see it. I didn't see it mentioned anywhere, and I didn't see it in the open rocket. I know
it's on the propulsion slide. You can see the.
Oh, I must be.
Yeah.
Yeah. All right. Yeah, the one thing that I would have mentioned there is just on the open racket, at least, it seems like your back centering ring is pretty far away from it. So just make sure that you can reach it for putting screws in. But that's it for me on 41. Next, I'm on 54, unless anyone's before me.
I got one on 46. Just on the number, like the layers of carbon fiber, was the 30 number correct?
Yeah, it was 30 layers of carbon fiber, and under a bit more like stringent, like very detailed oriented making of the fins, we could probably get more layers in there as well.
30 layers seems like a ton. Just
They're
solid,
tough.
just solid carbon fiber. Like, I guess, are you vacuuming it? I guess, are you getting any weight savings from using carbon fiber, or what? Ben told the old mechanical lead and I were looking at some of the slides last night, and he wanted me to bring up this one in particular. It just seems like a lot of the weight savings and strength you're getting from carbon fiber is being eliminated if using 30 layers of it.
Yes. So what I did is I measured what the actual fin was, and then comparatively to like last year, it's not all that much more. I would say just a little bit over last year's, and the fins this year are they're kind of they're smaller than I would like, but Open Rocket so far says that those numbers are all right. So yeah, but the weight is, I did make sure to measure it. I thought that was going to be a concern, definitely. It was like, I think like 25 grams, so like a tenth of a pound, something like that. On these fins, or like a little bit more than that.
No, with the resin, it's going to be way more than that.
Yeah. Okay.
But one thing to keep in mind is that your criteria here isn't weight savings; it's strength.
Yeah.
Your booster fins are sitting next to 70 pounds of propellant. So triple their weight, who cares, as long as they aren't going to fold or flutter. That's more important. But can you back up one slide to 45, please?
Yep.
I thought I must have heard, I thought I heard at one point that no pressure was being applied to the layers as they were being glued up.
I actually, while the presentation was going on, I realized I had misspoken. There is pressure, but not like a hydraulic press. There is the pressure of clamps. We're clamping it down with I think we use 5-6 clamps to clamp these two things together the entire time while it was curing. So there is some pressure. I misspoke.
And
these are small
pressure
enough
between the layers to get rid of any air bubbles and things is all you need, so that's fine. But if it were no pressure at all, I'd be concerned about air bubbles building up between all those layers.
Yeah, we did see there were a few surface air bubbles, and I was thinking potentially looking into the possibility of the team making kind of like a pressure chamber large enough to hold the jig of the fins, so that the beak would reduce the bubbles.
Or vacuum bagging could work as well. Go the opposite way. Instead of building up pressure, you create suction. And it's a lot cheaper to build.
Yeah.
Okay.
Yeah, my only comment with clamping would be just make sure you clamp until you know the resin is cured, because if you take it off before the resin's cured, it's not gonna be great.
Yeah, definitely.
Yeah, that's all. I'm next on 54, unless anyone's before me.
52, please.
Yeah, 52 as well.
There is no part of your rocket that is going to take more stress than this transition is. It has to be the strongest thing in your entire rocket. If you are not planning on foam encapsulating between the inner tube and your cone, you should really reconsider and foam encapsulate the entire thing. You just cannot make this thing strong enough, no matter what you do.
We did discuss that, right, John?
Yeah, we did. That's something we were looking into. Is there, based on your experience, is there any certain like type of foam or way that would best suit this?
Absolutely. And if you want to contact me after the fact, I'm happy to take you through several different recommendations for how you do that.
Okay, thank you.
Yeah, I know I've got that 2-part, I think it's the public missiles foam, I think, Rob, that we talked about before.
Yeah, the public missile stuff, though, isn't quite, it's a little too low temperature for desert use. We might need to go to a different style that has a little bit higher temperature tolerance, but there's several manufacturers out there.
Cool.
The one body cal coupler on both sides, is that on the 3-inch side? Is that 3 inches or 5 inches?
It's 3 inches into the dart.
Do you think that's enough, Robert? It just seems a little, maybe a little low.
More is always helpful, but 1 caliber is considered the standard. So, you know, I don't think anyone is going to tell you there's not enough there, but if you could, especially on the 3-inch side, if you could go to a caliber and a half or even 2 calibers, that would stand you in better stead, especially since you're not trying to worry about putting an engine into the dart.
Okay. Yeah, we'll look into that. Do you think there would be any negative effects that would come from too much friction between those 2 tubes with the increased caliber length? I mean, increased length of the coupler?
Sure, friction varies directly with surface area, so
Yes.
you just need to make sure that you're not over creating too much friction there. You have to be careful of that, especially again when you're testing that. You need to heat everything up so that it's the temperature it's going to be flying at instead of the temperature in Michigan in January.
Yep.
Yeah, that's what we were worried about. Do you have any, I guess, tips or techniques that you've used when you're launching, I guess, in different environments for couplers that separate?
The biggest thing is making sure that both halves of any couplers or any sliding components are made of the same thing. Because the minute you say that your body tube is carbon fiber and your coupler is fiberglass, now you're talking about different rates of expansion based on thermal variation, and something that you fit together that works really well at 40 degrees is going to be either clamped together permanently or fall apart at 140 degrees.
Okay.
Yeah, they're both fiberglass. It's fiberglass into fiberglass sections. So.
Yep.
And that's me on 54. My one thing is that your max speed is Mach 1.7. Above Mach 1, Open Rocket does not get very happy. And I think it does tell you that when you run the simulations, that the equations they use for aerodynamics are not optimal above Mach speeds. There is a program developed for it called RAS Aero. I think we've talked about it before. It's meant for anything above Mach. So I'd want to just run stuff through there. I haven't used it much myself. It seems very archaic to me, but it might get some use for you guys.
Okay, great.
I also have a copy of RockSim Pro, which will also handle simulations above Mach 1. So if you guys wanted to have me run that through RockSim, I could do that for you as well.
That would be awesome.
Yes, it would.
I'm on 63 for my next thing.
62.
I guess I had something here as well. Go ahead, Rob. We probably have the same thing.
Now, I appreciate this is just a symbolic illustration, so this may not be the issue that I think it is, but at the moment, your tender descenders are being shown at the very point where your shroud lines meet. If you're really planning to have your tender descenders that far away from your parachute, the point where it's reefing your chute for you, the odds of that reefing line successfully pulling through the base of your rocket go drastically downward because your chute is going to be spinning as it drops. It's just inevitable dropping that far. And if those two tender descender lines are the same length as your shroud lines, it's going to turn itself into one gigantic knot by the time you get to 1,500 feet and you actually try to release those tender descenders. They'll release for you just fine, but those lines aren't going to go anywhere because they'll be hopelessly knotted around your shrouds. But if your descenders are going to be up close to your rocket or much nearer than your illustration shows, then that's fine. You can help minimize that. But keep in mind, this whole thing is in a very violent spinning, turning environment as it's descending, and having multiple lines like that just greatly increases your likelihood that you're going to develop a snarl.
Oh, okay. So you're saying you'd recommend the tender descenders be near the avionics bay where it's connecting?
No, I'm not. In fact, I'm saying the exact opposite of that.
Oh.
What I'm saying is, if you're going to be running lines from your tender descenders up through the hem of your parachute in order to reef it and then back down again, and those tender descenders are as far away as the base of your shroud lines, your likelihood of getting that to successfully deploy is very small because the whole parachute is going to want to spin in circles as it descends while under reef. And that's going to cause your reefing lines, which are connected to your tender descenders, and your shroud lines to spin around each other. You want to try and avoid having multiple lines across the same distance when you're talking parachutes, especially for long duration drops like your apogee chute going down for your dart, because of the likelihood of spinning and the likelihood of tangling.
Okay. Yeah, because we did do the exact same thing that is here in the last rocket, and the dart one worked fine, but it was, like you were saying, kind of tangled up as it was going down. It kind of twisted itself together. So that's good. Do you have, like, I think that's why we have the slider, but I'm not entirely sure if it'll like manage the shroud lines well enough to mitigate what you're
yeah, the slider is really only going to make a difference for you at 1,500 feet when you're unreefing your chute. Other than that, your slider is going to be held up against the base of your chute anyways, and it's not really going to affect any of the period that I'm concerned about tangling occurred, that is between apogee and main deployment.
Okay.
But I'm happy to talk with you offline sometime to talk about mitigation options.
Yes, that'll be great. Thank you.
All right, and then your drogue chutes, I see that they're 18 inches in diameter. On the open rocket, they're 17 point whatever, if it was a calculated number. But when I ran these simulations, I saw the descent rate, right when the parachute is deploying, is at 200 feet per second. So I'm just wondering if those drogue chutes are appropriately sized. I know that each piece after motor burnout weighs about 18 pounds. My L3 after burnout was 24 pounds, and I ran it on a 30-inch chute for drogue. So I'm just wondering how you came up with that number, if it was a calculator or what.
Yeah, it was the calculator. I'm not sure if Open Rocket is plugged in properly. Hold on.
Yeah, and it might have just like the wrong drag coefficients and things on it. So I just looked that over and make sure that you got that correct there.
Yeah. Okay. It might have been before any weight changes happened, so that might have not been updated properly.
Okay, and I know the rocket is still light in Open Rocket too, which is why I was particularly concerned. because I think it's right on the cusp of being workable right now with that diameter. But if the rocket gets any heavier, then they're going to have to be upsized.
Yeah. Okay. Yeah, we'll make sure to update that and make sure the descent rates are proper.
Sure. And then my next thing is on the next slide about the factor of safety on the eye nuts. Is that a factor safety of one? Do you have two eye nuts at a Y harness there, or is it just one eye nut?
It's two eye nuts.
Okay.
So they're both combined, so the factor of safety should be more than that.
Okay. So each one should be able to support the load by itself?
Yeah.
Okay, gotcha. That's all I wanted to know.
My comment on this page was that because you're attaching the shock cords to quick links, keep in mind anytime you have shock cord meeting metal, you need to take the strength of your shock cord and cut it in half. It doesn't matter whether you're tying it, whether you're using a mattress suture like you're showing here or anything like that. The fact that you have your cord running through a metal loop, its breaking strength drops by about 50%.
Okay. Make sure to account.
And my next thing is on the next slide. With the smoke system, what material is this made out of? Is this enclosure 3D printed?
Yes, it's going to be made out of PET.
Okay. And do you have a smoke thing, like a smoke grenade in mind that you're using? I don't know. There's not many details on what the actual device is.
Yeah, we're currently working on that. It's like in the
yeah, because I'd be concerned with how cool something would burn. I guess smoke grenades. I know tear gas grenades get real hot, but I don't know about other smoke systems. I don't know if you built one, Rob.
I have. In fact, what I would tend to use in systems like this is just simply talcum powder or brightly colored, like chalk or something like that. Press it in there and let it come out on its own. But if you've got a low temperature, if you've got an idea in mind for a low temperature burning smoke system, that's great. Just make sure you test it so it doesn't melt your container.
All right. Definitely.
Okay, my next one is on 68.
Me too.
Yeah, so mine was for, let's see, the shear pin size. Are they 440s or what? The size isn't listed.
Yes, they are 440s.
Okay, they're 440s.
Good catch. I forgot to put that.
That was my question as well. The number of shear pins is irrelevant when you don't know what they're made of or what their diameter is.
Mm-hmm. Yeah.
Okay, my next one's on 76. So this last year, we also had the tele-GPS in the booster. We had one in the booster and one in the Dart. Same configuration where the Dart one was on top of the payload and where the tele-GPS in the booster was in this mount. And we only got packets from one of those GPSs. And after I thought about it more, this is the one that we didn't get packets from. And I did notice that the antenna for this GPS is right next to and running parallel to a steel threaded rod, which I'll leave that up to Matt, our resident RF expert, to explain. But I don't think that does any help for the signal. I don't know if it's the only cause of why we didn't get any packets last year, but I can't think of anything else different between the two systems.
Is this an issue of not getting packets or just getting packets but no GPS fix?
Well, I don't know if we got a connection.
I don't think we were getting packets at all. I think we got GPS fixes just fine where we got packets, but I think on the pad we just weren't getting packets.
Yeah, if I remember correctly, we were getting a few stuff getting sent, but nothing was able to form a packet for the booster. But then after a while, we stopped even getting that. So that threaded rod may have not helped, but it could have also been a potential issue where the battery died, because I know Aaron didn't have them very much charged at all. And
well,
especially after going back
I did
out.
check the batteries, and they were fully charged. They were both at the same rate. And I've just finished building my add-ons for my egg finder system, and it says, all over it, don't run it right next to a threaded rod. Don't run it right next to a threaded rod.
I see.
I'm not sure the threaded rod on its own would absolutely murder the signal, but it definitely didn't help things. And combined with poor terrain, I could see that obstructing the signal pretty badly.
Right.
Yeah, the GPS only showed being on the launch pad for the booster, Josh. So it only ever showed that coordinate, and then it never showed any others.
Yeah. Which is abnormal because usually you would get it more when you go in the air. Was the big thing.
Right.
But
And that's
yeah,
the
the reason they
legendary
put that the
axis.
disclaimer on there is any kind of parasitic element, any kind of metal like that that you put in the near field of the antenna is going to become part of the antenna system. It'll act like a reflector or a director and alter the radiation pattern, which is maybe why you were able to get packets when it was on the launch pad, but as soon as it went up in the air, now all of a sudden you didn't.
Sure.
So one thing you could do, I mean, with a setup like this, is you could run tests like that. You know, just go ahead and even on the ground, just make sure that okay, you're getting reasonable signal strength. Like all the rotate the part all the way around and make sure you're getting reasonable signal strength all the way around. If you're not, then you got something that's altering the radiation pattern of the antenna because
Yeah. Also, on that note, if you're going to do a test like that, you probably also want to change the elevation that your receiver is at compared to the transmitter, because in real life, that rocket's going to be very much above you for most of its lifetime. So you'll make sure you're getting a signal going kind of downwards too.
Yes,
Yeah,
agreed.
This one I think is about at head level. I don't think it's much higher than that.
Well, yeah, I just mean like once it's in the air though, it's going to be so far above you that you're going to want to be
Yeah.
testing like on the ground that you're getting a signal, not directly parallel with the antenna, but at like pretty steep angles from it.
Yeah, I'm with it. You put it on top of the parking garage and measure from castle.
Yeah. You don't have to go that extreme, but something along those lines would be helpful. Yes.
All right, that's all I had on the tele GPS. My next
I got
one is
stuff
on
on 88.
77.
I don't know if you got stuff before that.
I'm on
77.
77.
All right.
All right. Do you want to go first, Rob? This time I went
Sure.
first last time.
Just asking your eye nuts at the top and bottom are connected to a common threaded rod that runs through the bay?
Yeah.
Okay. Then keep in mind the snacks forces are exactly identical because the minute the weak one gives, it's just going to pull the threaded rod out of the other end. So having one stronger than the other isn't useful.
Mm-hmm.
Yeah, so we'll have to mitigate that. Probably have to do some redesigning of this to make sure that the parachutes don't pull through the 3D print, and to also account for the GPS. So we'll have to look back at this and figure out a solution.
There are also very simple ways to build shock absorption into the system using nylon tubes. And if you guys are interested in trying to mitigate some of the shock loads on your bays, shoot me an email and I'm happy to try and explain it for you.
Okay.
Yeah.
Thank you.
All right. I'm on 78. Okay, this one, I think it was this one at least, where, yeah, body tube lipo charger connector. Is there going to be a connector sticking out of the side of the rocket, or is it just embedded in a hole?
That was that was an idea. It's not. I'm not entirely sure if we will do it yet, but that's a good.
Okay, and there's so much battery life on those tele GPS batteries. I don't know the circumstance where that's going to be too useful, especially because it seems like the bay is very easily removed. I know that this last time we just removed them real quick and charged up the batteries when we needed to. Because I just wouldn't want anything sticking out, especially a piece of plastic sticking out when you're going Mach 1.8. I know that I embedded my switches in the walls of my L3. The switch caps are just gone off the top of them.
Yeah.
Yeah, so speed is not a joke there. Next, I'm on 86. If no one's before me. Seems like I win. Okay. My question was just on the mount in the top right. Are there 4 boards? I don't know how many boards there are.
That's actually a battery mount.
Yeah,
There's
there's
4 batteries. There's 2 for the tele-GPS and 2 for the experiment board.
Okay, gotcha. They just looked real thin, like board slots to me.
Yeah.
Yeah,
It's pretty similar to our design.
Okay. Yeah. Okay. Then no question there then.
Okay.
88
unless,
is my next one.
Yeah, unless you're just someone's about to say 87, I've got 88 as well.
Yeah, 88.
Okay, Rob, you want to go first? Because I'm probably just going to talk about electrical things that aren't relevant to you anyways.
Okay. Where are your strain gauges actually going to be mounted? Are they on the nose cone where the payload bay is, or down on the body?
They're on the body, below the nose cone.
Okay. That's what I was curious about, because obviously the nose cone being a cone shape is going to be inherently much more rigid than a body tube is. And if you want to get meaningful numbers out of your strain gauge, putting them on the body makes a lot more sense.
Yep. Thank you.
Yeah, the main goal is almost centrally right. Yeah, so you can get the bending moment as well.
Yep.
Which will be good.
All right. If Rob's all set, then my main comment was that the setup for the strain gauges is a little bit odd. I see that you do correctly mention having them there to compensate for thermal drift, which makes sense. You should do that. The main issue is that, from what I recall, with a strain gauge, if you want to compensate like that, you generally want to have one of the strain gauges on something that's not going to be moving significantly. So it's basically just a reference of how does this strain gauge behave nominally with temperature drift and like no other changes. Whereas what you're describing is giving them 2 basically completely different loads, which I'm not sure, unless you have some other resources that I'm not aware of on strain gauges that explains this, I'm not sure it's going to work how you expect.
Okay. Yeah, we looked into the method you're mentioning. I think that's a quarter bridge type 2, where you have a one of the gauges is not measuring loading, but it does measure the thermal. Our issue was, how do you correctly measure that thermal strain when it's not right up against the body tube, and what kind of difference would you have there with the thermal strain? And
frankly, if you want my answer, I would suggest in this use case, maybe it might not even be worth trying to compensate thermally on the strain gauges analog. You might just want to have a calibration routine in software so you can see basically prior to launch what your readings are and calibrate based on the offset that you're getting before there's any real strain on the body tubes.
That's not a bad idea.
Okay, yeah, we'll look into that. And the idea was with, the one strain gauge that's mounted transversely would measure that transverse strain, and if we were able to determine through testing that Poisson ratio, then we could relate that to, well, yeah, the issue. I see the issue, but we'll figure that out and see if we can determine a way to make it work with this configuration, or if it'd be better to do it with a single active strain gauge.
Okay, sounds good.
Also, I think from what I understand, so if you're running, I could be absolutely wrong with this, but if you're running the strain gauges in the formation that you have, you'd want them to be measuring these same things, because technically you have one vertical and one horizontal as a temperature offset. I think they're supposed to be running the same direction.
Well, if you have them measuring the same same direction, then you'll just double the thermal strain.
Yeah, the idea is you want them to cancel out. You want basically the idea with having multiple strain gauges is that they should have the same thermal drift. So you want one of them set up so that it is compensating for the thermal drift, but you're not messing up your intended measurement with it.
I see. All right, sorry about that.
So I guess it's kind of I don't know if it's implied here, but that means you've got like two of these strain gauge circuits, one measuring the strain, measuring axial strain, and the other measuring transverse strain.
The idea was just to measure the axial strain, parallel with the rocket. So
you got so basically there's just one circuit, and you've got one gauge mounted in the axial axis, and the other one in the transverse axis.
As of right now, yes.
So with this, how would you distinguish between this circuit? You're not going to be able to distinguish between the two unless one of them is really generating, is generating little to no strain at all.
Okay.
And I think that we will see a much higher, axial strain during launch over any radial or anything like that.
Okay, but again, realize that with that, if that's the way you guys have this built, you will not be able to distinguish between the two.
Yeah.
That was kind of what I was trying to ask. Just I didn't put it very well.
So
Right.
yeah, we'll have
Yeah,
to
and that's
review and come back and see where we can make this better. The issue is like with a half bridge configuration, the optimal way is to have one gauge on the inner surface and one gauge on the outer surface, but we can't exactly put in one of the gauges on the outer surface.
That won't work.
So we have to come up with a solution for that, and doing one active gauge might be better in trying to plan for that thermal strain. So we'll discuss that. And
yeah, another option is I'm not sure if this would actually be the case, but if you were able to expect that the temperature at the PCB is very similar to the temperature actually on like the wall of the body tube, it probably wouldn't actually be that hard to experimentally generate a calibration curve for the strain gauges, just like on the ground, and then it's just easy software compensation again.
Right, you would need like you need an environmental chamber or something like that in order to run the calibration. I don't know. Do you guys have one of those?
Not our team doesn't personally, but
well, I mean, the university. I would think they might.
I'm sure there's. Yeah, we'd have to ask around, but I'm sure there's somewhere on campus in one of the labs that we could access.
At the very minimum, by doing that, you could at least see, how much it is actually changing, and if it is, and it's repeatable, like what Matt said, you could probably build like you could build a calibration table that would all you would have to do is measure temperature, and you know how much you'd have to compensate the reading.
Yeah, and that also brings me to another good point, which is that depending on the magnitude of the readings that you're getting, the temperature drift might even be negligible error to you anyways, and you can just ignore it and move on with your day.
Yep, that could be the awesome outcome.
Yeah.
The blind squirrel finding the acorn type outcome.
That would be ideal. We just need to do some testing. We haven't gotten to that point yet, so if we can test and see that it's negligible, then yeah, that's the best outcome.
All right. Well, I would love to give more comments. I know I'm getting ready to head out here at 8.
Yeah, I think 8's going to be the limit, and then from there we can have.
I know that there's still a bunch of comments that people have. I know especially Matt's document. Matt and friends have stuff.
You're welcome.
I'll just read my last couple things out loud real quick, and then I'm going to start getting to go. My one thing was for the real-time data for the payload on 98, where your antenna is going to be. Your payload is solid steel. So just make sure that you find a place that's not solid steel to put that. On 97, you've got 20 millisecond reads on a lot of your data sources. So you're reading in all that data every 20 milliseconds. It seems very fast. I don't know if all of your sensors can, one, support it, or two, whether you need that much data. And it's going to take
what slide did you say?
That's 97.
97?
There's a bit. It might not be 97. It looks
yeah, it's
like.
Probably changed.
It's somewhere around there.
Lucas put a similar comment on 99.
Yeah.
Yeah. And then one on 109 for your Nucleo on the ground, being powered by 2 batteries in parallel.
Oh yeah, I mentioned that one too.
you can just power off of USB, I believe.
Also, you don't even need a Nucleo. There are literal USB adapters for XBs because they're just serial communications. It's literally just a USB to UART converter on a board that the XB slots into.
Yeah, those boards are supposed to be what you program them into, I think, or how you set
Well,
it.
yeah, they get programmed with AT commands, which is basically send it string over serial, it does thing. So you can program them from anything, but they do have dedicated software for your desktop computer that you can easily configure them with by plugging them in over USB like that.
Yes.
Yeah.
And also answer
And I
your
got-
question, Andre, we do have a couple of them already.
Yeah, I saw them.
And then I got one more thing before I get going. Is your PyCam V2 on slide 112? You're talking about 1080p 60 FPS. There is no Pi camera in existence that can do 1080p 60 FPS. Most you could do is I think 720 at 60. And if you get up to 1080p 60 FPS, it's very hard on your storage capacity. So keep that in mind. And then the last thing is about the Coletta Air sponsorship. I'm the contact for that. So if you want it again, let me know.
Yes, we'll do. Thank you, Justin.
Yep.
All right. I'm gonna be honest. I only
luck,
have like
guys.
one substantive
you.
comment that Justin didn't already just mention. Actually, no, I have two. So, real quick, 103, you're talking about using shielded cabling for the strain gauges. Good job trying to avoid noise in them. Shielded cabling doesn't really make the most sense in this application, especially if you meant something like a coax. You probably just want to do a twisted pair so that you have a very small loop and call it a day is probably going to be the easiest, best solution in this context. And then a little bit earlier on 100, that harbor block diagram definitely needs some work. It has a lot of parts that just kind of go nowhere that should be in between different things like the current sensor, and it's not very clear what some parts of the harbor diagram are for, such as what the 5-volt rail is required for, or what is using the 3.3-volt rail of a buck on there versus what's using stuff from the STM32 directly, or if the STM32 is being powered by which rail, things like that. And that's pretty much it on my end.
Okay, perfect. Thank you so much.
Yep, thank you.
May I add a couple more real quick comments?
Of course.
On slide 94, you talk about changing possibly over to 400 megahertz. Make sure you're double checking the documentation and requirements of the launch, simply because at least last year there was a requirement of staying at 900 megahertz. And you'll want to make sure that the rules allow you to go to that range if you're looking to do it.
I think Erin made a comment about that too in her notes for you guys.
Yeah.
The last thing is the level 1 CERT class and the flight out on November 19th at the LK airport. Has anybody let Team 1 know that you guys are coming out?
No, that's something I actually need to do.
Okay.
That's a
Just
good
because
reminder. Thank you.
chances are a late November Team 1 launch is probably going to be fairly lightly attended, and they may not be ready to help 20 people get their level 1 certs.
Yes,
If
that's
you
a good
find
point.
that that's the case and they're having trouble getting people out there, somebody please let me know and I'll be happy to come out and I can help process paperwork and stuff.
Oh yeah, we would really appreciate that. Yes, Sierra, do you want to say something? Sorry.
Oh, I was just going to say that we did do this at the same time last year, and unfortunately the weather made it so we couldn't get everyone certified, so we're hoping that that doesn't happen again.
Yeah.
Yeah, I think I forwarded Norm's information over to you, Devin. If not, then let me know.
Okay. Sounds good.
Hey, one other note too on this: if you guys are intending on changing down, changing down to like the 400. Why, when you say 400 megahertz, you probably mean like the 70 centimeter amateur band. You will have to change the antenna length.
Yeah, and Michael, this was at 400 megahertz before. Yeah.
Yeah, 400 megahertz is what they ran it last year. I guess one quick question I've been meaning to ask Matt, but I've never had an opportunity to. It's something that should be fairly quick. I'm not the most familiar with EMC, and because I'm taking the class right now. What's considered as the near field is when it's less than like the lambda over 6 from like the antenna. And I think, at least just to throw it out there, if that's the case, then that's about 4.5 to 5 inches, depending on exactly what frequency we are assigned to.
Just to throw that out there for those who need to know.
Okay, cool. All right, thanks, Josh. Okay, thank you everyone for attending. We really appreciate all the help. We couldn't build this rocket without our advising members and the alumni and everyone. So we really appreciate you guys coming. Don't forget to fill out the rubric. And is there any other comments or questions?
Lucas left a few of them, but he left. But I could just
Okay.
cover them tomorrow.
Yeah, of course. All right, great. Thank you so much, everyone. Have a great night.
Thank you.
Thank
Good
you.
night.
Have a good night.
Thank you.
Thank you.
Yeah.